When dealing with balanced three-phase systems, understanding the National Electrical Code, or NEC, requirements for neutral conductor sizing is crucial. In a balanced three-phase system, the neutral conductor can sometimes be sized smaller than the phase conductors, but there are specific conditions that must be met. Firstly, the neutral current must not be greater than 20% of the phase current. Secondly, the neutral conductor must be protected by an overcurrent protection device rated not greater than the ampacity of the neutral conductor. It's important to determine if your system qualifies for these exceptions before reducing the neutral conductor size. In the situation of boosting from 120/208 volts 3-phase 4-wire to 230 volt 3-phase 3-wire using 3 transformers connected in a Y configuration, with the H4 from each transformer connected to the source neutral, several factors come into play. It's noted that the load is 3-phase, which implies a balanced load across the phases. In such a balanced system, the neutral current is unlikely to exceed 20% of the phase current. However, there's another important consideration within the NEC. It states that for 3-phase systems, the neutral conductor should be sized not less than 1/3 the ampacity of the largest phase conductor, as found in NEC Article 310.15. 3. While the code doesn't explicitly mandate that the neutral conductor be the same size as the phase conductors in a balanced 3-phase system, it is generally a sound practice to size the neutral conductor to at least 1/3 the ampacity of the largest phase conductor to ensure safety and compliance. Now let's apply this to the scenario. If the phase conductors are 1/0, then the neutral conductor should be at least 1/3 of the ampacity of 1/0. Based on standard ampacity tables, 1/0 copper conductors typically have an ampacity of around 150 amps at 75 degrees Celsius. Therefore, the neutral conductor should have an ampacity of at least 1/3 of 150 amps, which is 50 amps. Looking at standard wire sizes, a number 4/0 copper conductor would be required to meet the minimum ampacity requirement. It is generally recommended to replace the number 10 neutral conductors with the number 4/0 to ensure compliance with the NEC and provide adequate protection for the neutral circuit. Sizing the neutral conductor properly is a critical aspect of electrical installations, especially in 3-phase systems. The NEC provides guidelines to ensure safety and prevent overloading of the neutral conductor. While the code permits reducing the neutral conductor size under specific conditions, it also mandates a minimum size based on the ampacity of the phase conductors. This dual requirement ensures that the neutral conductor can safely carry any anticipated imbalanced current while also providing a path for fault currents. Firstly, consider the system balance. In a perfectly balanced 3-phase system, the neutral current is theoretically 0. However, real-world systems are never perfectly balanced due to variations in load impedance and distribution. Therefore, a neutral conductor is always necessary to carry any unbalanced current. The NEC allows for a reduced neutral size if the neutral current is not more than 20% of the phase current. This condition recognizes that in many balanced systems, the neutral current is significantly lower than the phase currents, allowing for a smaller conductor size without compromising safety. Secondly, evaluate the overcurrent protection. The neutral conductor must be protected by an overcurrent protection device, such as a circuit breaker or fuse, that is rated not greater than the ampacity of the neutral conductor. This ensures that the neutral conductor is protected from overload conditions that could lead to overheating and potential fire hazards. The overcurrent protection device should be selected based on the ampacity of the neutral conductor, taking into account any derating factors for ambient temperature or conductor bundling. Thirdly, adhere to the minimum size requirement. Even if the neutral current is less than 20% of the phase current and the overcurrent protection is adequate, the NEC requires that the neutral conductor be at least 1/3 the ampacity of the largest phase conductor. This requirement serves as a baseline to ensure that the neutral conductor is sufficiently sized to handle potential fault currents and imbalanced loads. The 1/3 rule provides a margin of safety and helps prevent the neutral conductor from becoming overloaded, especially in situations where the system balance may fluctuate. Now let's delve into the practical implications. Consider a three-phase system with 1/0 AWG copper phase conductors. According to the NEC, 1/0 AWG copper conductors typically have an ampacity of 150 amps at 75 degrees Celsius. To determine the minimum size of the neutral conductor, we need to calculate 1/3 of the phase conductor ampacity. 1/3 of 150 amps is 50 amps. Therefore, the neutral conductor must have an ampacity of at least 50 amps. Looking at standard wire sizes, a number 6 AWG copper conductor has an ampacity of 55 amps at 75 degrees Celsius, which would meet the minimum requirement. However, it's important to consider any derating factors that may apply. If the conductors are installed in a conduit with other current-carrying conductors, the ampacity may need to be derated according to NEC Table 310.15. B. If the ampacity is derated to below 50 amps, a larger conductor size would be required. Next, let's think about voltage drop. Voltage drop is another important consideration when sizing neutral conductors. Excessive voltage drop can lead to reduced equipment performance, overheating, and potential damage. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the length of the conductor, the current flowing through it, and the conductor's resistance. The resistance of a conductor depends on its material, size, and temperature. The voltage drop can be calculated using the following formula: voltage drop equals current times resistance times length. If the calculated voltage drop exceeds the recommended limits, a larger conductor size may be necessary to reduce the resistance and minimize voltage drop. We should also discuss grounding and bonding. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault currents to flow back to the source, tripping the overcurrent protection device and preventing electrical shock hazards. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of voltage differences and shock hazards. The NEC requires that the neutral conductor be grounded at the service entrance and at the source of separately derived systems such as transformers and generators. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. Bonding conductors must be sized according to NEC Table 250.102, based on the size of the circuit conductors. Now let's consider harmonics. Harmonics are non-sinusoidal currents and voltages that can be generated by nonlinear loads, such as electronic equipment and variable frequency drives. Harmonics can cause overheating of neutral conductors, especially in three-phase systems with a high percentage of nonlinear loads. The NEC requires that the neutral conductor be sized to carry the harmonic currents in systems where the nonlinear load exceeds certain thresholds. In some cases, it may be necessary to increase the size of the neutral conductor to 200% of the phase conductor ampacity to accommodate harmonic currents. In conclusion, proper sizing of neutral conductors is crucial for electrical safety and system performance. The NEC provides guidelines for sizing neutral conductors based on system balance, overcurrent protection, and minimum size requirements. It's important to consider factors such as voltage drop, grounding, bonding, and harmonics when sizing neutral conductors. By following the NEC guidelines and considering these factors, you can ensure that the neutral conductor is adequately sized to handle any anticipated currents and provide a safe and reliable electrical system. Finally, when dealing with boost transformers and relocating equipment, it is always best practice to consult with a qualified electrical engineer or a licensed electrician to ensure that the electrical system is properly designed and installed according to all applicable codes and standards.